Oh, do we remember what we did last time? No. So we talked about the fact that graphs keep going on forever and ever. Yes? Do you remember that? And they repeat. Do we remember how often that the sine rule repeats? Every what number of degrees? Every what number of degrees does the sine rule repeat? No, Rihanna, you want to know? Yeah. Good. Every 360 degrees. Okay, so it takes 360 degrees to do one cycle, and then it just keeps going on and on and on and on. Yes? And there's symmetry that we can find lots of different solutions. Okay? Or what about the tan graph? How often does the tan graph repeat? Are you just doing exercise? No. By putting the hand up and then taking it?
I thought I knew the answer.
Let's give it a bash.
No, because it's small.
Oh, okay.
Because I thought it's not on the graph. I don't know what it's on there.
So how often does the tan graph repeat?
180.
180, every 180. And how about the cos graph? Emily? 360. Brilliant. Okay? Now, what's the name of that thing when we say how long does it take to do it? Did I say it already?
Yeah.
Lily? What is it? The period. Yeah, so that's how long it takes to do one cycle. Okay? We said period. Right, do we remember? Sorry, how high up does the cos and the sine graph go? I'm asking this. In a way, I'm trying to not say the actual words. DNA. 1. So it goes up to 1 and down to -1. Do you remember that? The sine and the cosine both go up to 1 and down to -1. What do we call that feature of the graph? Kiara? The amplitude. Oh, we're loving this. Does the tan graph have a certain amplitude? No, it keeps going on and on forever. If you have a value in front of an equation for a sine graph or a tan graph or a cos graph, what happens to it? Really? Be careful. If you've got a number in front of it, it doesn't shift up. You know?
Does the amplitude increase?
The amplitude changes. Remember? So when you have a number in front of it, it stretches it.
Okay.
Yes?
Yes.
Do we remember that or not? Emma?
Yes, I do want to that or thinner.
Gets taller and thinner. Nice. Okay, so it pulls itself up. If we have a number stuck on the end, Lily, what happens to it?
Oh, then it goes poopy.
Oh.
I mean,
Maybe I didn't want to ask you. It shifts up or down. So the whole graph would shift up or down depending on the value. Okay?
comment sounds like you're teaching about this all.
If there's a number in front of the x, what is affected? So if we've got sine of 4x or sine of a half x, what happens to the graph? What is affected when there is a number stuck in here? Jamie, reading that?
Yeah. It changes the period.
It changes the period of it. Okay, so if we had sine 4x, it would tell us that it would do its normal cycle 4 times as fast. So in the normal 360 degrees, you'd actually have 4 of the sine graphs. Okay? Pardon? Now, when it comes to the questions that are going to come up on these, it's difficult to know, and this is one of the new features in this syllabus. So they haven't really looked at the sine, cos, and tan graphs very much in the past, or the other graphs that we're going to look at. So it's tricky for us to know exactly what kind of questions could come up. I have printed off some questions for us to have a look at, to give us an idea. It's like an official textbook for the course. But as long as, so I wouldn't stress too much about doing lots and lots of work on these. I think it's more going to be recognizing features of it rather than learning lots of intricate information about the sine, cos, and tan graphs. Okay? I don't know if I've made that word or better. Alright, that's another one. So now, sometimes lots of variables are going to change, okay? So if we look at a graph, it could be that the amplitude has changed, it's shifted up, and the period has also changed, okay? So all of these things that we need to have a look at. So this graph here, to find the equation of it, we would look at all the different features. So first of all, can we kind of see where the central line for this graph is? So remember, it's halfway between the top and the bottom. So what value is the very top? That's equally a 5, yep. What value is the bottom? 1. So where is halfway?
3. Oh,
Yeah? Okay, so if the top is at 5 and the bottom is at 1, then halfway of that is going to be at 3. So that's where our central line is. Having identified our central line, that often helps to find our features as well. So, what would our amplitude be? 2. Nice. We know our new central line is at positive 3. Let's have a look at our periods. Well, actually, first of all, we should be examining if it's a sine or cos graph. Is this on a sine or a cos? Why cos, Gabrielle? Because it does the C on the y-axis. Remember that? Remember that little trick? So this one does the C on the y-axis, so that's a cos curve. So how long is their period? How long does it take to do one full cycle for this graph? Emma? 360. Awesome. Now that means that our value of C is just 1. Yes, because we know that if our period is 360, there is no coefficient of x.
Why is the amplitude?
Because we know that from our central line up to the top, or the central line down to the bottom, is a value of 2. Yeah? So then we can put all of that information together, and we know our equation is y equals what? Where do our numbers go? What number goes first? Do you remember?
At cos, and then 1. Right?
Not quite, because our amplitude has changed.
Wait.
Say, Brianna?
I didn't say anything.
Oh, who said it? Was it Elena? I knew back there, sorry. 2 cos. Do we have anything in front of our x? No, because our value of c is just 1. So we've got 2 cos x. But our central line has moved, so we've got a plus 3. Does that make sense?
No.
So our amplitude is the A. Our new central line is the, I think I put it as B. And this is our C. We're talking about A, sine or cos, and Cx plus B. Okay, how about that? So our A goes at the front. So our value of A is our amplitude. So that's why the 2 came first. Sine and cos is which type of graph it is. And I've only done sine and cos because they're the most common ones. The C is our value here. So that was just a 1. So we just had x. And then our B value is where our central line was. Does that make sense? Yeah? Okay, so you're obviously going to have to catch this up later. Clearly you decide the sign. Alright. Okay, so this last thing is that we've talked about our graphs going up and down, but do you recall when we had our parabolas? So when we had our x squared graph, this was down here at -5, that would have been an x squared minus 5, yeah? Remember that? If I had one over here that went through the value of 6, what would I know that the equation of that graph would be? Do we remember?
X plus 6.
Almost.
X squared. X squared.
Not
6.
Not plus 6.
Squared? Oh, minus.
X
Minus 6.
6 all squared. Okay? vaguely remember that?
Yeah.
I was saying to that one. I think. Bless you. No, was it Hitchcock? You hungry? Alright, so numbers that are stuck on the end, remember, shift them up and down. This number is inside the brackets and is being squared. Okay? So that means that our graph isn't going to shift up and down, it's going to shift left and right. And it goes to the opposite direction than we would imagine. So if we're going to +6, then in the bracket it will have a -6. So if I had a graph over here at -3, the equation of this graph would be x plus 3 all squared. Okay? Alright? Every other place. So the value that it goes to is the opposite of where it would be. So if I had this situation here, it's a similar kind of thing. I am taking the sign of the value of x plus theta. I'm taking the cos of the value of x plus theta. I'm taking the tan of it. So we're actually having the value of theta inside the bracket. Now this indicates that it's going to be a horizontal shift. So I was trying to make it clear to you the other day as well. We can always relate this back to the quadratic graphs because the features of these changes that we're making have the same effect on any kind of function. So it doesn't matter what kind of function it is, if we stick a number on the end of it, it's going to shift it up and down. If we're going to stick a number in a bracket and apply that value to the actual function, it's going to shift it left and right. If we stick a number in front of it, it's going to stretch it. Okay, so all of these features or transformations of the function affect any kind of graph, not just the trig graphs or the quadratic graphs. Now, I've said here, choose a familiar point of the graph and see how it's shifted. That's going to normally help you determine this value here. Okay, so what I've got here is not helpful. All right, so the first one here is my which kind of graph? That's my cos. Okay, and this baby here is my sine, yes? Okay, because it's done the s through and this is done the cos through. So this blue curve can be described either using sine or cos. Because we did decide or establish earlier that they are just shifts of each other, aren't they? Okay, so this cos curve is exactly the same, it's just shifted slightly. So if we were trying to describe the blue curve as a cos curve, okay, so a cos. Normally, our cos curve would cross here up at 1 and at 0. Oh, that wasn't the right place. Where is this? Oh, for goodness sake. Where is this here? Okay, this was at 0. Where is this place now? How much has it shifted? Has it shifted left or right, and by how many degrees?
45.
It's gone right 45 degrees. So can we all see that? Okay, so the cos curve has shifted right by 45 degrees. Now we know that a right way shift, or a shift to the right, means that it's going to be a negative value. Yes, you're happy with that? So because it's shifted to the right, it means that it's going to be a negative value here, and it's going to be negative 45 because our graph has shifted to the right 45 degrees. Yes? Well, let's have a little look, see. So look at the sine curve. So if we were going to say it was a sine curve, again, you're trying to find a good point that you can see how many degrees it's gone across. I'm going to focus on this part here. This is at 0, and I can see this is now over here. Yes? Is that good one? I mean, if you want to still look at the top of it, you can. Either way, I hope that you'll see that it's gone now left 45 degrees. Yes? So my equation for this one would be x plus 45.
Why is it?
Because you only know that degrees. And because when we're using the sine, cos, and tan button, we have to put an angle measure in there. Okay? So ideally, everybody starts with another angle measure with radian, but you're sticking to the degrees.
Okay.
Alright? And that's why before any exam or test, you should always make sure your calculator is in degree mode. Now we did reset them all initially to be in degrees for the default, so hopefully they stay that way. Do we all understand that? Oh.